This work is a little bit older, but it's on conservation law type system, so I thought it would be appropriate to talk about it here. In particular, I'll be talking about anomalous dissipation and spontaneous stochasticity in the Burger's equation. So what are these two things, anomalous dissipation and spontaneous stochasticity? Well, our real motivation is to understand incompressible Navier-Stokes turbulence. And so that's, you consider a velocity u that solves Navier-Stokes, which is divergence-free. And Navier-Stokes solutions dissipate kinetic energy globally. So if you write down a balance equation for the kinetic energy, the time rate of change is just depleted by the action of viscosity converting kinetic energy into heating. A remarkable experimental and numerical observation is that if you look in the limit of zero viscosity of the rate of energy dissipation, it tends to a constant non-zero. So this is what you can see in this plot here. This is an accumulation of a bunch of numerical simulation data by Kaneda et al. It just shows as Reynolds number increases, which you can think of like 1 over the viscosity, the dissipation rate goes to something that's not zero. And if you stare at the dissipation rate, you'll see that the only way for this to happen is if in the limit of zero viscosity, the fluid velocity is no longer differentiable. The gradients have to blow up. And if you indeed look at turbulent flows, you see that as it becomes more and more turbulent, fluid velocity is becoming more irregular. But Lars Onsager, sometime before 1945, figured out a more refined statement about the regularity consistent with this observation. He said that fluid velocity could have at most a third of a derivative. And he was talking in the particular sense of a Holder type condition. It couldn't have any Holder condition with an exponent greater or equal to a third. So this is what anomalous dissipation is. Do we see this type of regularity in turbulent fluids? Well, the answer is yes. If you look at velocity increments, it satisfies this scaling relation from data and experiments in a range of scales between a viscous cutoff and an outer length scale L. You see a Holder type condition being satisfied. So the increment scales with x minus x prime to h, a fractional exponent. And if you're below the viscous cutoff, the velocity is smooth. So it's Lifshitz there. This could be said another way in terms of energy spectrum, which is often more common in turbulence. This type of spatial structure corresponds to an energy spectrum that has a power law type behavior in K in the inertial range with the exponent related to the Holder exponent of the field and an exponential decay for wave numbers higher than the cutoff wave number. And so if H is exactly a third, which is Onsager's conjectured regularity threshold, then this corresponds to the famous Kolmogorov 1941 theory of turbulence, where the energy spectrum decreases like k to the minus 5/3. And here's just some data from the JHU turbulence database that shows this type of behavior for the spectrum. So you have this region where you have power law type slope with minus 5/3 and then exponential decay. So that's one interesting property of fluid turbulence. There's another one, which is that it's an extremely effective mixer. And this is perhaps best quantified by an observation made by Louis Frye Richardson in 1926. He was studying particle pairs in a turbulent flow, for example, soot particles in a volcano plume, and he figured out from experimental data that these pairs would separate according to a t cubed power. So pairs of particles on average will grow like t cubed away from each other. The crucial aspect of this observation is that nowhere do you see a dependence on how far those particles started out initially. And this is actually really important. We'll come back to it. But let's first try to make a simple toy model to understand this behavior. Well, so combining with what we said before about anomalous dissipation, let's think about particles in an ideal Kolmogorov velocity where the velocity increments actually scale like the distance to the power 1/3. You can think of this as a toy model for high Reynolds number turbulence. Then the separation grows simply, the rate of change is given by the relative velocity, which in this model we know explicitly. And we can solve this ODE, and we get this solution right here. If you stare at that and you look at long enough times, we see that all initial conditions have the same long time behavior. And it's a T-cubed behavior. So the particle pairs separate like T-cubed, and they forget the initial separations they had. So this is exactly the type of phenomenon Richardson saw, but here in the toy model we can really understand what the source is. And it's this peculiar feature, which is that if you start particles at the very same point, at finite time they'll split to finite distances. So particles have L0, 0, and they split to finite distances. And this is actually not so surprising because this example here is really the textbook example of non-uniqueness in ODEs. The right-hand side is not Lifshitz. It's only Holder continuous with exponent to third, and there need not be unique solutions. And in this case, there aren't. But that's the hallmark of forgetting the initial configuration is indicative that there's perhaps this non-uniqueness phenomenon in the underlying ODE. So first, do we see this in data? And the answer is yes. Richardson looked at experimental data in the 1920s, but here's some high-resolution isotropic turbulence data done more recently. And you can see the different colors correspond to different initial separations of pairs of particles. And time goes on, and all these particle pairs converge to the same T-cubed behavior at long times. And importantly, the initial separations seem to be forgotten. There are two plots here. One of them's at higher Reynolds number, plotting the same thing, but it's non-dimensionalized by scales that are becoming increasingly smaller. So what these show in conjunction is that as you go to higher Reynolds number or smaller viscosity, particles can start out closer and yet split to finite distances faster. So extrapolating in the inviscid limit, you might expect it happens instantaneously for particles starting at the same point. Okay, so actually it's lucky I spoke after Alexei because he talked about exactly this phenomenon in the context of PDEs. Here, this is exactly the spontaneous stochasticity for ODEs. So just to put it together, if you have a velocity field satisfying a Holder type condition with an exponent h, if h is 1, then it's Lifshitz, and you know that there's a unique solution to equation 1, the particle trajectory equation. But if h is between 0 and 1, there can in general be infinitely many solutions. And for turbulent fields, h is less than or equal to a third, so we're outside the realm of standard uniqueness theory. But you could regularize the first equation by adding either a smoothing or a random noise and make sense of, for example, a random solution. If you add an additive Brownian motion, then you can show that there's a unique stochastic solution. And if the field is smooth, as you take that regularization away, so the zero noise limit, you, with probability 1, converge to the unique solution of equation 1. And if h is fractional, then this doesn't have to happen, and you can converge to a non-trivial probability distribution on the space of non-unique solutions of equation 1. So this is spontaneous stochasticity. You're deterministic up to a blow-up point, and then you continue as a random solution. And it was discovered in the Kreikner model by Christoph Goetsky, Bernard, and Kupiainen. So that was a bunch of words. Here's a picture of what's going on. If there's no spontaneous stochasticity and there's a unique solution, let's draw that as the black curve. As you take the noise away, almost every realization will converge to the unique solution of the underlying deterministic equation. On the other hand, if there are non-unique solutions, as you decrease the noise, different realizations will clump around different non-unique solutions, and it can impose a probability of going one way or another. So this is what's going on. And Goetzky and Vergasola in 2000 conjectured that these two interesting properties of hydrodynamic turbulence, anomalous dissipation and spontaneous stochasticity, are actually intimately linked. So they say there seems to be a strong relation between the behavior of the Lagrangian trajectories and the basic hydrodynamic properties of fully developed turbulent flows. We expect the appearance of non-unique trajectories in the infinite Reynolds number limit to be responsible for the dissipative anomaly. So the goal of this talk is to really prove this conjecture for the Burgers equation. For Navier-Stokes, it's far off, but for Burgers we can really show it and give some insights into Navier-Stokes from that. Okay, so let's just remind everybody what the Burgers equation is. This is inviscid Burgers. It's just fluid self-advection with no pressure. And of course, it shocks. So profiles steepen until they become multivalued, and at that point, you develop a shock. At least the entropy solution continues as a shock. And the reason why this happens is that particles in a Burgers field are just freely flying. There's no acceleration on them. So they travel in straight lines and transport the velocity along those lines. And since they don't know each other, they eventually intersect, transporting multiple values of velocity to a point. So here you can see this sort of Lagrangian picture of the blowup. We'd like to study the Lagrangian picture in the inviscid limit to make contact with spontaneous stochasticity and Navier-Stokes turbulence. And it turns out there's a very beautiful work by Peter Constantine and Gautam Ear that shows you can generate stochastic Lagrangian representations for fluid equations. So if you add a viscosity term to Burgers, well, then you have unique global solutions to that equation. And you can actually write out what that solution is in terms of particles that are moving along with the flow and kicked by an additive Brownian motion. So this was that regularization I put on a few slides ago, but here it's motivated in the sense that you can get an exact representation using such trajectories. And so the procedure is, at any space-time point x and t, you generate a bunch of curves that follow the fluid velocity at previous times and are kicked by noise until they sample the initial surface, where you average them and pick up the Burgers velocity there. So it's essentially just a generalization of the method of characteristics for viscous Burgers. And if you know the Feynman-Katz formula, it's a nonlinear Feynman-Katz representation for fluid equations. So the question we'd like to answer is, what's the zero viscosity limit of Burgers, and how is it related to the zero viscosity limit of this stochastic representation and zero noise on the trajectory? So I should begin by saying that Denise Bernard and Bauer in 1999 studied spontaneous stochasticity for Burgers, and they concluded that it didn't exist. So they, in particular, studied the forward flow of particle trajectories, and they found that particles follow the velocity, and when they hit a shock, they follow the shock velocity, and they stick to the shock forever. And this has since been generalized by Kunin and Sobolevsky. And because of this uniqueness they find for particles forward in time, they concluded that there was no spontaneous stochasticity. But this result is not true if you think about particles traveling backwards in time, which is exactly what's necessary for constructing the Burgers velocity with the Constantine-Ear representation. So we'll prove it here. To do this, we have to restrict ourselves to potential flow, so where the Burgers velocity is a gradient of some function phi. And then we can actually write down an explicit formula for the transition probability for a particle going from point x at time t to point A at some time s less than t. And you have to do a little bit of work, but you can write this out in terms of an action functional s, which involves just this potential function and well, a couple of other terms. But the point is it's actually a good large deviation rate functional, and you can study the inviscid limit of this model and pick up just contributions from the zeros. So just a remark, the Constantinian representation is just now, in the language of this transition density, an integration against that kernel of the velocity at a previous time. So from what I said before, you can study as sort of a large deviations property of that transition probability and prove that as measures, these transition densities converge weakly as viscosity goes to 0. And what you get is very simple. If x at time t is a point of regularity for the inviscid Burger's equation, then these transition densities just converge to delta functions that follow the straight line characteristics of the inviscid Burger solution. On the other hand, if x is on a shock at the inviscid Burger solution, then you converge to probability 1/2 of splitting on the two Lagrangian trajectories that enter at that shock point. So here's a picture of the shock surface, and you can see backwards in time there are two trajectories leaving at any point there. And so this is spontaneous stochasticity in the sense that you're no longer continuing as a unique deterministic flow, but instead you have a probability of splitting one way or another. The Constantinian representation just becomes an average over these two directions, which gives you that the shock moves with 1/2 left-right velocity, the average of the left and right velocity, which is just the Rankine-Hugoniot jump condition. And the lax entropy condition is actually implicit in the entire formulation, since it's coming from the zero viscosity limit. So I'll skip, that's just an example using the Koklov sawtooth solution, but I'll just skip to how this explains the dissipative anomaly in Burgers. So for Burgers, it's actually true that you dissipate all convex functions of the velocity, not just the energy. So you can write down a balance equation for the rate of change of psi of u, any convex function, and that's strictly dissipated by the viscous dynamics. And in the inviscid limit, the entropy solutions dissipate these convex functions. And we'd like to understand how that dissipation is related to the probabilistic splitting of particles. In order to do that, we can work out a purely Lagrangian representation for this dissipation. So the left-hand side of this second expression here is just the difference between this convex energy at a final time and the initial time. And it's given by a sum of two terms that involve only contribution from shocks. So there are these two integral terms over the shocked interval. So what I mean by that is that at point xt, it's the interval on the real line that's mapped to that shock. And the first term is just integrating the contribution of that energy from the initial velocity in that interval. And the second term is the same procedure, but where you replace that initial velocity with an apparent velocity that would yield all the particles hitting at the shock point immediately at x and t. So you can see here, these are particle trajectories. In the real system, they hit along the shock previously to x and t, and they continue on as a shock. But the second picture, they're all meeting at x at time t. And so from this formula, there's an interpretation of anomalous dissipation as a loss of information. So you're replacing the information on the Burger's velocity that you don't know because it fell into the shock with this uniform distribution, and by doing so, you're actually depleting the convex energies. Okay, but again, we'd like to connect this to this Lagrangian splitting. So to do that, we can write down, just take the derivative of the previous expression and get an evolution for the energy. And it's sourced by this right-hand side involving two terms. We want to show that this is a negative contribution to argue that the energy is decreasing. So the red term here is something called a Bregman divergence, which is strictly positive. So it contributes the right sign to the dissipation. And the question is, why is that blue term negative? So why is this whole dynamics dissipative? And so using the spontaneous stochasticity, we can write the shock velocity as the sum of the right and left velocities in average. And after some manipulation using the information about particle trajectories, we get to this expression that the shock velocity is just given as this uniform average of the velocity within the shock interval. And then directly by Jensen's inequality, this expression in blue is shown to be strictly negative. So therefore, the dissipativity or negativity of the conservation law anomaly is due, in this case, to spontaneous stochasticity. So it's sort of the conjecture of Goedzki and Vergasola for burgers is proved. So just in conclusion, I want to draw some connections to Navier-Stokes turbulence and to think about what we've learned. While the zero viscosity Burger solution has this property that forward particles coalesce and stick together, they have a unique evolution, but backward you have this dispersion or splitting, and it's non-unique. So this very strong time asymmetry of particle dispersion actually gives you anomalous dissipation for Burgers. And again, it's in support of this conjecture by Goedzki and Vergasola. For 3D Navier-Stokes, one also sees a time asymmetry in particle dispersion. These are these measurements of Richardson, but you can do them both forward and backward in time, and you see that particles spread faster backward in time than forward in time for 3D turbulence. And in 3D turbulence, you observe anomalous dissipation, so energy is lost. On the other hand, in two-dimensional turbulence, you sort of observe the opposite phenomena. You have a cascade of energy to large scales, which indicates that energy is sort of anomalously created in a certain sense and propagates up. And you see exactly the opposite tendency of trajectories. So they spread faster forward in time than backward in time. And so we conjecture sort of as a lesson from the Burgers case that the sign of the anomaly is related to the time asymmetry of particle dispersion. And so that's a subject for future work. But yeah, thank you.
Questions? So with regard to Burgers equation,
Yeah.
what you refer to as conservation law anomaly, is that entropy production? Is that what you mean?
Yeah, and yeah.
Would you want to say that dissipation is actually stochastic, spontaneous stochasticity backward in time, right? So it's not forward.
Right, or at least that the asymmetry between the backwards, because in 3D Navier-Stokes you would expect spontaneous stochasticity both forward and backwards in time.
But
But
is it just vision from a Burgers equation, or you have some more general?
It's Burgers and lessons from the passive scalar models, but yeah.
Another question? Let's thanks to the speaker again.